concentration, we're usually talking about some mass per unit volume. For every little bit of mass this loses, it loses some volume. So overall, the concentration of that solid never changes, stays constant. Hence, solids and pure liquids are excluded from equilibrium expressions. We do nothing with them. Liquids are treated the same way. This is the way your book goes at it. There are other reasons why this happens that we won't go into, but there's actually a lot more behind the equilibrium expression. This is the base reason though. This concentration of that solid never changes because it lost some volume and lost some mass, so its concentration stayed the same. So it doesn't, all we're worried about in equilibrium, what's changing in concentration? It's not. So when you get a problem like this, or they ask you to describe an equilibrium like this, when you go to write your K equals products over reactants, quickly look through the reaction and look for anything pure solid or pure liquid. If you see it, ignore it. For example, here, liquid water isn't going to show up in the expression at all. It's not included. So now you have to write the remaining products over reactants. On the product side, we have hydrogen ion. We have bicarbonate ion. We have our CO2 that started it.
Oh, aqueouses are included with this one?
Aqueous are always included. Yep. And that would be the proper equilibrium. So you'll start to see, and we'll see equilibrium constants in all guises. First thing you do when you go to write the expression, look for the pure solids, look for the pure liquids, ignore them. Second way you can tell, as we get into the deeper problems, you'll notice that in the problem itself, when they give you the reaction, they have to tell you some things about the concentrations. The pure solids and the pure liquids, no data is going to show up. They're just going to walk around like it's not there. That's telling you. It's the other reason they're telling you. Ignore it. You don't need to worry about it.
How come the aqueuses are included but liquids aren't? I thought aqueous was a liquid.
Aqueous means that is floating in a liquid.
Oh.
So it is in a different, is in a suspended media of water. That's why it's important. And that changes, that can change concentration. Arguably, almost everything we do in equilibrium relates around gases and aqueous species. It's really the bulk of it.
I don't mean to get off track, but why is aqueous accepted into a reaction if the straight up water is not? Like, wouldn't that water become part of the equation?
No, because what happens is if you really go in, and you're actually going to unfortunately see this in lab. In the lab experiment you're going to do next week, you were scheduled to do labs 7 and 8. If you look at that lab, you're supposed to set up some samples, they sit for a week, and then you do them the next week. Since you didn't have that Thursday lab, or the Tuesday lab, those samples are already made up. I made them for you. So what's going to happen is you're going to go in to do lab, and you will have done buckets already because I did it for you. Because to make the samples, all you're doing is putting 3 things in a bucket. That's no rocket science. I'm putting 3 things in a bucket. The reaction has to sit for a week. That's why I had to do it the last week so that you have it next week, so it's had the time to react. When you see it on Tuesday night, they will make you calculate the water, but it's kind of a waste of time at the end because the value, all it does is change the scale of the reaction, but in essence, water is present here, water is still present here because this is all floating in it. Nothing happened to the water on either side of that reaction.
Okay.
So it's just...
So it does kind of get included into the equation just kind of sneakily.
It gets included actually when you look at the concentration because you're measuring how much water it's measured in. So it's in from that side. That's where it actually shows up. But it does nothing in the reaction. This reaction, the water is just simply the media. It's just like the beaker that it's floating in. But don't be thrown off. I want to make sure I tell you this. When you do the lab on Tuesday night, you're going to see that they have you work with the water. Just go with it. Just go with it. It really doesn't matter. It really shouldn't be there. But if I was doing the lab with you, yeah, I can call them out, but I don't want to screw anything up. Just calculate the number. Now,
Question.
go ahead.
What, have you actually done this experiment?
These kinds?
Yeah.
Oh yeah,
So do you include the water?
I do. as I know numerically, but when you look at the number, when you look at that experiment, and you see the number you're gonna get, all the water does is change the scale of the number. The number, the reaction number is being multiplied by something that really isn't involved. It doesn't affect, it still allows you to look at the reaction. I believe they included it, they left it there, so that if you hadn't seen equilibrium before you got to that experiment, they wouldn't have to explain why it's not there, why something that's in a reaction isn't there. That's why I believe Bill, when he wrote the lab, left it in there. Usually we get to this lecture right before it, and when we get to the experiment, I just skip that column and move on. It doesn't change anything, it's one more little calculation that you'll do. But it's completely legal to throw it out. All right, go.
How do you know the CO2 is heavier? Why is it on the bottom?
Oh, CO2, it's all, remember, it's products over reactants.
Right.
Reactants
Yeah,
over-
how's, because it's going like both ways, you know, like I'm,
Great question, actually. Equilibrium constants, when they're written, are written for the forward reaction, the arrow going to the right,
okay,
always. Great question, exactly. That's what it's for. That's how you know.
okay.
All right. Calculating equilibrium constants. Let's take a look at how we find these numbers. The easiest way to do that, we're going to start with a problem. We'll do problem 665. We're going to look at how we lay out these problems. We're looking at problem 14.5. Which has a bunch of data that we have to look at. I'm going to lay out a method to solving equilibrium problems. There are multiple types of equilibrium problems. The first one is the easiest of the ones, but they're going to follow similar patterns or similar things we do every time. You'll be able to spot by the end of tonight which one's which. And by the end of tonight, I'm going to teach you a trick to get around the harder one if we can. All right. 16.5. First things first, we're given a reaction. And then we look at what they tell us. They tell us a little bit of data. We have to be a little careful what they tell us. First thing we're sure of, it's a balanced chemical reaction. Before we go anywhere, it's balanced. We don't have to mess around with it. Second thing we do every time, write the equilibrium. Go ahead.
Sorry, what page is this on? I didn't bring my textbook today,
That's
so I
okay.
want to look at it when I get home.
665.
Okay.
665. Second thing we do, just write your equilibrium constant. Just write numerically what it would be. Well, it would be the CH3OH over CO over the H2 squared. Then we look at what they tell us. They tell us that in the reaction, the initial concentration of CO is 0.27 molar and H2 is 0.49 molar. The only way we can keep track of the data that they're going to toss at us is something called an ICE table. And the ICE table stands for initial change equilibrium. Initial change equilibrium. That table, and you see it laid out in the book, allows us to follow the reaction and see what happens. If we write that, we write initial change equilibrium. Then we write that on the vertical. On the horizontal, write the reaction. Write what's in the reaction. CO plus 2H2 goes to CH3OH. Now, once you frame an ICE table, take a look at, what did they tell us? They said that the initial concentrations of CO, initial, is 0.27. They said the initial concentration of the hydrogen is 0.49. The next comment they say is at equilibrium, the concentration of CH3OH is 0.11 molar. This is our equilibrium line. It's the CH3OH. So what they give you in these types of problems are something about the beginning, something about the end. We need to get between the two. The change in this is the line that is usually the tricky part. Saying nothing else, if they tell you nothing else, this reaction, these two things were put together. The initial concentration of CH3OH, if they say nothing about it, you assume that before you put the reaction together, none of the product was there. Can't be there until the reaction starts. First one we have to make an assumption is there's none of that there. They didn't say the initial concentration of methanol, CH3OH, was something. Nothing was there. Now we have enough to figure out the table. If this started at 0 and ends at 0.11, the change in this one has to be plus 0.11. The only way to get there, right? How to make that a much to get from 0 to where we're at. When you have that, we then have to figure out what we're going to put here, 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 here. Because really, in the end of this, we needed the equilibrium line, because that's what's going to go in that expression we just built. So let's take a look. The stoichiometry between this guy and this guy is 1 to 1. For every 1 CO, you get 1 CH3. The change in this, therefore, has to be the same as the change in that. 1 to 1. If you're making 0.1 over here, you have to lose 0.11 on that. It's negative because it's on the reactant side. Reactants are going away, products are gaining. Use your arrow as your dividing line. If the stoichiometry of this guy is 2, what's the number goes in the box for that one? 0.22, because you get 2 for 1, minus 0.22. You're using 2 of those for every one of the other one that you're making. Now we can walk down the columns and just look at the numbers. 0.27 minus 0.11 gives us 0.16. 0.49 minus 0.22 gives me 0.27. That's an ice table that's filled out. Remember, the numbers we need for the math to figure out Kc come from right here. One of the things you can check when you're doing these, don't forget the minuses. Anything that is to the left of the arrows are minus, anything to the right are added. Now we know what the concentration of everything at equilibrium is. They're the 3 numbers we need to find out what K is. Let's take the numbers and put them up here. Kc. Concentration CH3OH, 0.11. 0.16. 0.27. Don't forget square. Good.
You lost me. How do you know that those numbers get the same? Like, how do you know that you're basing it off of the 0.11?
Because it's the only one that we know something about. They told us this one, they told us this one.
Mhm.
So we had to figure this one out. Once we know this one, we can finish the rest.
The C is 1, okay, but then with the H,